Hello, everybody. My name is Gang Liu, an independent researcher in Kingston, Ontario. Today, I'd like to talk about a general equation of state and its physical origin and its physical meaning. I will have the following 8 sections. The first is the fundamentals of the equation of state, then forms and derivations, then the physical origin, or the physical foundation of the equation of state. In other words, what is the physics behind it? That is the macroscopic mechanical equilibrium condition. In physical meaning, the equation of state describes quasi-equilibrium thermodynamic processes. Then, the equation of state is presented in the form of Newtonian dynamics, followed by calculation examples. Then, the equation of state is generalized from periodic structures to any materials with periodic boundary condition applied. At the end is a summary. Let's start from the fundamentals. The equation of state, abbreviated as EOS, was studied as early as in the mid-17th century. As a comparison, the great book, Philosophiae Naturalis Principia Mathematica, was published in 1687. What is the equation of state? A simple answer: an equation to determine the volume of a fixed amount of matter and an arbitrarily given external pressure and temperature. The word arbitrarily above means that the external pressure and temperature may change with time. However, at a given point of time, the external pressure and temperature are fixed, and therefore the volume predicted by the equation of state is fixed as well. For example, the equation of state is expected to give us the volume of 2 kg oxygen of water and an external pressure of 25 atmospheres and a temperature of 80 degrees Celsius. Then the equation of state should be an equation relating the volume, external pressure, external temperature, and other variables about the matter explicitly or implicitly. So, the equation of state gives us the fixed volume of a certain amount of matter and given external conditions. In fact, it is already known that any matter is made of macroscopic particles. If we imagine that the sun, all planets, and all other objects in the solar system are macroscopic particles, how do we define the volume of the solar system? And is this newly defined volume fixed under the same real external conditions? In fact, for a system of a limited number of macroscopic particles, the volume is not needed, because all the particles' positions and other physical properties can be calculated in principle by applying Newtonian dynamics or quantum mechanics. Then every detail is known. We therefore don't require an equation of state either. So, the equation of state is only needed for systems with a large number of macroscopic particles, when the system as a whole can be considered as macroscopic matter. Now, let us consider the fact that the volumes of the system may be different between an equilibrium state and a non-equilibrium state, and may be different between different non-equilibrium states. Then, the equation of state is meaningful only for the macroscopic matter in a macroscopic equilibrium state, because the equation of state only gives us the fixed volume. This reveals the physical content of the equation of state. We will come back to this later. Forms and derivations of the equation of state. The equation of state for an ideal gas is presented in almost all related books. PV equals to nRT, where P is the external pressure, V is the volume of the gas, N is the amount of the gas in moles, R is the universal gas constant, and T is the absolute temperature. This equation is also called the ideal gas law. Only applies to ideal gases. The van der Waals equation is also a well-known equation of state, and shown in many books as in the following expression. It has two matter-specific parameters, A and B. They are usually determined by fitting experimental data for certain ranges of external pressure and temperature. It is often used for gases and liquids. There are many other empirical forms of the equation of state. However, let us only focus on rigorously derived ones and their physics. Now let us consider crystals. A crystal is a macroscopic body of matter made of a three-dimensional periodic arrangements of exactly the same cells. The number of cells in any direction is large enough to be considered infinite. Each cell contains the same finite number of microscopic particles, and is imagined to be a parallelepiped with a certain shape and volume. Since crystal is essentially an unlimited periodic structure, let us call the edge vectors of the parallelepiped cell the period vectors. Crystal structure is another important research field, studied extensively and closely related to the equation of state. The task of it is to determine the positions of all macroscopic particles inside the cell and the crystal period vectors. This is usually achieved through X-ray diffraction experiments. From pure theory point of view, the particles' positions can be calculated by applying the Newtonian dynamics or quantum mechanics. Then, what is the theory to calculate the period vectors? Since the crystal period vectors determine the shape and the volume of the cell, the equation determinum is actually the equation of state of the crystal. The equation of state for crystals under isotropic pressure is for the situation where the external pressure acting on the crystal is the same from all directions. The rigorous theoretical equation of state is presented in almost all related textbooks, with the assumption that the cell shape is null and does not change, as the following equation number 7. In equation 7, beta is 1 over kt, and k, z, and v are the Boltzmann constant, the system partition function, and the cell volume, respectively. However, there are situations where the external pressure is not the same in all directions. The cell shape may also change, or may not even be known beforehand. The piezoelectricity and piezomagnetism are so fascinating that electric or magnetic field may be created by simply applying mechanical forces on certain crystals. For that purpose, be sure to apply an additional pressure on the crystal, but only in one direction, while keeping the pressure perpendicular to it remain unchanged. For a crystal of piezoelectric or piezomagnetic property, let us apply external balanced forces from the top and the bottom. Then the crystal becomes shorter and fatter, and an electric or magnetic field across it emerges, shown as the red lines. So here, the external pressure is not the same in all directions, and the cell shape should also change. Therefore, the equation of state for unique pressure, equation 7, cannot apply here, as it can accept only one pressure value. Actually, crystals may experience more complicated external forces that even include components parallel to the crystal surfaces. Such complicated external forces can be described by the so-called stress. Then, what is stress? Let us recall pressure first. Pressure is the normal force per unit area. Roughly speaking, stress is the total force acting on the surface per unit area vector. Since the total force and the unit area are both vectors, the stress is expressed as a second-rank tensor, or 3x3 matrix. Then the force by the stress S acting on the area vector sigma of a surface is the dot product of S and sigma. In order to keep a crystal in an equilibrium state, the external stress must be symmetric. For the special case of the same pressure P in all directions, the stress S reduces to S equal to minus Pi, with I being an identity tensor. A crystal is made of the same cells periodically, where the red ones are the period vectors. If external balanced forces or symmetric stress are applied, shown as orange arrows, the crystal is deformed and the red period vectors are changed. As shown in the previous simulation, the period vectors may change independently according to the external stress applied. A paper published recently in the European Physical Journal PLOS, EPJP, recently derived a new equation to determine the period vectors for crystals and arbitrary external stress and temperature based on the principles of statistical physics. How it was done? Let us first recall how the equation of state for crystals and a unique pressure was derived. The first step was to express the work done by the external pressure equivalently on the crystal cell as dW equal to minus P dV. Then the equation of state can be obtained immediately as the following equation number 7. Please note, here we use the same equation numbers in the EPJP paper. As a matter of fact, the following is a widely used principle in statistical physics. If the work done by external forces on a system may be written in the form A1 dB1 plus A2 dB2 plus etc., then for any pair of variables AI and BI, we have the following equation. It is used 3 times in this reference book. The equation of state for the same pressure in all directions, that is equation 7, was derived from this principle. In order to derive our equation for period vector H equals to A or B or C, let us introduce the corresponding surface area vectors of the cell as sigma A, sigma B, and sigma C. Then, the work done by the external stress S equivalently on the crystal cell can be written as the following equation number 1, where S dot sigma H is the external force acting on the cell surface sigma H, and dH is the displacement of that surface. Based on the above principle of statistical physics, we can immediately get the following equation number 2 as the equation to determine the period vectors for any external stress. Since the volume of the cell is determined by the crystal period vectors, equation number 2, determining the crystal period vectors, is the equation of state for crystals and arbitrary external stress and temperature. Of course, the special case of the isotropic pressure is covered. Now let us talk about the physical foundation or physical origin of the equation of state. In other words, what is the physics behind it? As we talked earlier in this presentation, the equation of state is meaningful only for macroscopic matter in a macroscopic equilibrium state. Since in the macroscopic equilibrium state, the macroscopic mechanical equilibrium condition MMEC applies. From another point of view, once the independent period vectors and all positions of particles in the cell are known, everything about the crystal is determined. In other words, these are the degrees of freedom of the system. In principle, the positions of the particles in the cell may be determined by Newton's dynamics or quantum mechanics. The period vectors are the only degrees of freedom left to be determined. In fact, the macroscopic mechanical equilibrium condition can completely determine the period vectors. Once all the degrees of freedom of the crystal are determined, no additional independent equation is needed or even permitted. However, on the other hand, the equation of state is rigorously derived. Since the equation of state and the macroscopic mechanical equilibrium condition are both for determining the period vectors, they should be essentially the same. Further, considering that the macroscopic mechanical equilibrium condition is drawn immediately from Newton's second law, more fundamental with a straightforward physics picture, it can be regarded as the foundation of the equation of state in physics theory. This also means that if the equation of state is not satisfied, the system cannot be in an equilibrium state. If the equation of state is written in the form of external stress plus x equal to 0, according to the macroscopic mechanical equilibrium condition, the internal stress balances the external stress. The second-rank tensor x should be the internal stress. For example, the equation of state for an ideal gas may be rewritten as P equals to 1 over V nRT. Then the right side should be the opposite value of the internal stress. Similarly, the right side of the equation of state for a unique pressure, equation number 7, also means the opposite value of the internal pressure of the system. In 2010, Tuckerman introduced the internal stress for crystals in his book, as in the following equation number 9. Combining Tuckerman's internal stress with our equation of state, equation number 2, we get equation number 11, which means equation number 12. So, our equation of state is the macroscopic mechanical equilibrium condition. The internal stress balances the external stress, and our equation of state and the internal stress Tuckerman introduced are consistent with each other. From the thermodynamical point of view, there is another equilibrium condition. It is satisfied, assuming that the temperature everywhere in the matter is equal to the external one. Let's see what it can do in physics. Let us suppose that the macroscopic shape and the volume of a given crystal are determined by the crystal period vectors. Then, our equation of state, equation number 2, determining the period vectors, determines the geometry of the crystal and any external stress and temperature. It therefore describes the thermodynamic quasi-equilibrium processes of the crystal, including expansions due to external forces and/or temperature. The corresponding coefficients and constants may also be calculated theoretically. For a thermodynamic quasi-equilibrium process, if external stress or temperature causes the period vectors to change from AI, BI, CI to AF, BF, CF, the work done by the external stress on the cell may be expressed as the following equation number 13. It is based on the previous equation number 1. And the total heat that needs to be supplied to the crystal in this process is expressed as equation number 14, where the initial and the final internal energies are ETI and ETF respectively. Piezoelectric, piezomagnetic processes. When an additional pressure is applied along a specific direction, the crystal period vectors change. The equation number 2 can be used to calculate these vectors and therefore the new crystal structure. Since the new electric or magnetic field should be created by the new structure of the crystal, this equation of state may help studying these phenomena. At constant temperature, the equation of state, equation number 2, may be used to calculate the crystal period vectors for a given external stress. When the external stress changes, we can recalculate the period vectors. If the change in the period vectors is proportional to the change of the external stress, we are observing the process by Hooke's law. Since both changes of the period vectors and the external stress are available in theory now, the elastic constants for the law can be calculated. The classical physics form of the equation of state. The partition function z in the equation of state, equation number 2, has definitions both in classical physics and quantum mechanics. Therefore, the equation of state can take either form. We will not discuss the specific form for quantum mechanics in this presentation. For the form in classical physics, we will take another straightforward approach. Molecular dynamics simulation is a very active research field that is closely related to the equation of state. It usually applies Newtonian dynamics throughout. It is common to apply periodic boundary conditions, i.e., to describe the system as if it were a periodic structure. The corresponding period vectors need to be dynamically simulated or determined. Much effort has been made to derive such dynamics. For that purpose, the paper published in the Canadian Journal of Physics cuts the periodic system into a left part and a right part with respect to the period vector h. Then applies the Newton's second law on the right part. Result: the following dynamical equation in the form of Newton's second law for the period vectors was obtained. Here is the internal stress introduced, and other symbols used there. For all particles in the cell, the rigorous Newton's second law still applies. When all accelerations are set to 0, the dynamical equation of the period vectors becomes the Newtonian dynamical form of the equation of state of the system, as it is the macroscopic mechanical equilibrium condition in classical physics. The internal stress plus the external stress equal to 0. And here is the internal stress pi. Actually, the above derivation has been carried out specifically with pair potentials only. The following publication deals with many-body interactions for the dynamics of the period vectors. Just a reminder, the velocities of individual particles in the cell are usually regarded as temperature-related random motion. However, the velocities of the period vectors reflect the deformations of the crystal and are therefore collective, i.e. ordered motions. These have nothing to do with the temperature. Calculation examples. In 2010, Ma and Tuckerman applied the quantum mechanical form of the equation of state to the study of a silicon crystal and isotropic pressure in the following paper. The EPJP paper employed the Newtonian dynamical form of the equation of state to the study of thermodynamic quasi-equilibrium processes in a one-dimensional crystal. Compression or expansion by external forces at constant temperature, elastic constants for Hooke's law, and the crystal breaking point were calculated. Heating from external temperature at constant external forces and the crystal melting point were calculated. The breaking and the melting points were calculated based on the fact that the macroscopic mechanical equilibrium condition cannot be satisfied beyond them. Generation of the equation of state from periodic structure to with periodic boundary condition applied. While equation number 2 applies to periodic systems, any limited gas, liquid, or non-crystal solid may experience external forces on their surfaces. In such a situation, the macroscopic particles at the boundaries experience the external forces directly, while the interior particles not. Then, they should be treated differently in the dynamics and the partition function. This may impose further difficulties in the calculation. To solve this problem, periodic boundary conditions are often used. Then, the system gets a complete periodic structure and becomes a crystal. Here is a cup of cranberry juice. In order to simulate this liquid, the boundary condition imposed by the cup and the air can be replaced with the periodic boundary condition. For this, a parallel pipette of the liquid is chosen as the simulated system. Then, the periodic boundary condition is applied, like this. As a result, the liquid becomes a crystal. More importantly, the real external forces on the original surfaces are equivalently replaced with the forces from the new imagined surrounding cells. So all macroscopic particles are now in the same environment and can be treated the same way in dynamics and partition function. Under these circumstances, equation number 2 and all conclusions based on it apply. Although both equation number 2 and equation number 7 apply to periodic systems or systems with periodic boundary conditions applied when they are under the same external pressure in all directions. The former has 9 coupled scalar equations, while the latter is only 1. The latter is actually a linear combination of the former scalar equations. So the former is more detailed than the latter and implies the latter. Let us summarize. The equation number 2 is the equation of state for any macroscopic matter with a periodic structure and periodic boundary conditions. It applies to any external mechanical conditions described by the stress. It is the macroscopic mechanical equilibrium condition. It can describe quasi-equilibrium thermodynamic processes, including expansions from external heat or forces, those governed by the Hooke's law and those related to the piezoelectric, piezomagnetic phenomena. And it may take either forms of the classical physics or quantum mechanics. Thank you very much for your attention, and have a nice day.